the story of computer science has been developing one abstraction on top of another, each of which makes us more powerful and empowers us to build better and better applications that extend the reach of computer science and extend the reach of humanity. And so I think really this is a story of success that's going to continue. And the way that we manage it is we climb this rising level of abstraction. I don't think it's going to take away our jobs. I think it's going to enable us to do new things that we couldn't imagine before that's going to create more and more value.
This is Sachin.
And this is Eric.
Welcome to Luminary, kitchen table style conversations with some of the world's brightest minds exploring boundaries of human knowledge.
Join us on a pursuit to transmit intuition and ideas. Find us at luminary.fm or on Twitter at luminaryfm. We'd love to hear from you. Today's guest is Jonathan Aldrich, a professor at Carnegie Mellon University and director of the Software Engineering Ph.D. program at Carnegie Mellon's Institute for Software Research. Jonathan's research focuses on software scalability. His work aims to improve software quality and programmer productivity through an interdisciplinary approach to software design. He has received the National Science Foundation Career Award and the Dahl-Nygaard Prize.
In our conversation with Jonathan, we cover his journey into research and academia, the evolution of programming languages, characteristics of the ideal programming language, as well as ways to measure software quality. He calls for a multi-disciplinary approach to designing programming languages. Jonathan also shares his recent research in building programming languages for writing web, mobile, and blockchain applications.
I would love to hear about your journey into academia and why you're at CMU today.
I guess it started when, actually in a summer internship, I was working for Sequent Computer Systems back, I guess, the summer after high school. I got an internship there. I worked for an amazing woman named Luigi Anderson. She's a Ph.D. from University of Washington, which eventually became my alma mater. But I worked on benchmarking object-oriented databases. And so I was looking at it both in C++ and Smalltalk. And so I learned the language Smalltalk, and I learned this idea of, we don't have to look at files as strings of bytes. We can look at them as object stores. And I learned the idea of a high-level language. And this was completely transformative for me. I think even learning C++ was really cool. But then when I saw Smalltalk, I realized, wow, how much power there is in being able to express design at a higher level. And so I got excited about languages from early on. I did my undergraduate at Caltech. They actually had a pretty small program then, very few professors in computer science, but I managed to take a advanced compilers class from Mary Hall, who was visiting at the time, and a little bit of software engineering class. And but I didn't really get a chance to. I sort of was dreaming and thinking about languages all the time. I didn't get a really chance to explore them until I went to graduate school at University of Washington, where I worked with Craig Ambers. And I think my journey into research was sort of interesting because I was full of these ideas, but many young people, I didn't really know how to make arguments about not just, this is a new cool idea, but this is an idea that has some. It's a bigger intellectual idea, right? It's novel research, right? How do you make an argument about that? So I had to kind of learn about how to do that with kind of a starter research project, which I did in compilers. But in the meantime, I took this class I went to the seminar on software engineering there, which David Notkin led, and I learned about, one semester we read a bunch of papers on software architecture, which is an idea that was developed here at Carnegie Mellon by David Garland, Mary Shaw, as well as others elsewhere. And I was just it was right about the time where I was kind of in the midst of coding on this compiler project, and the compiler was written in my advisor's weird language, so a very cool language, but unusual. In this language, you could put methods anywhere you wanted to. They didn't have to be in a class together with the data structure. And so this was very flexible, but it made things hard to find. And so this idea of software architecture was incredibly compelling to me. So I realized this is something that I want. I want to see software architecture, but I don't want it just to be a diagram on a whiteboard. I want it to be in the code. And so that's where I got my thesis idea and a research theme that kind of carried me forward, which is how do we incorporate ideas about the design of software into code so that we can check those ideas, so we can help programmers get the design right, and that we can ultimately build software that does great things for people.
That's great. How did you develop an interest for software and programming languages? Maybe even take a step back from where you were at Caltech, even before that.
It's a good question. I was lucky, I was fortunate to have my dad get me a Apple IIc computer when I was young, I don't know, 8, 9 years old, something like that. It came with some games and productivity applications and so on, but it also came with a disk on programming in BASIC. And so at some point, I got bored with whatever video game I was playing, and I stuck that disk in and learned to write my first little program. And then I did that for, I guess, and basically until I was through my sophomore year of high school, right? Programming in BASIC. It was sort of more interesting. A few games, like I wrote a club application for the little club that I was with my friends. And then I learned, I was switching schools, and the new school I was going to had a computer science class. And I said, well, I know how to program, but to get into the second class, I need to know how to program in Pascal. I said, well, I'll learn Pascal over the summer. And that was probably my first revelation about the power that a different language can give to you. Pascal, maybe long in the tooth still today, but it's a great design, right? It's a beautiful design for the kind of thing that it is. And I realized how much more power there was in the ability to organize things and express things at a higher level. And then, from there, I learned, I think in that class, or maybe in the next one at my high school, I learned C++ and the object-oriented paradigm, and I realized how powerful the idea of objects that simulate the world is. Objects in the computer representing objects in the world, and we can build virtual realities out of this. And that's what we do in software to some extent, right? Of course, I was thinking of games at the time. When we build software, we are building some representation of the world, or maybe a world that we want to create inside the computer, and that's always been inspiring to me. But I think languages are also what enable that, right? They give us that spark and that expressiveness of building the world as we want it to be.
Yeah, that's quite fascinating. Going from BASIC to Pascal to C++ to understanding concepts of object orientation. Pretty cool.
Tell us about the Institute for Software Research, your work there and goals of the institution, the mission.
So CMU's history in computer science goes way back. We got our first computer in the basement of the business school here, where Herb Simon was working with various colleagues. And he quickly realized the power of computing. Herb Simon is one of these polymaths, right? I believe he is probably the only person who has a Nobel Prize in economics in this case, and a Turing Award. Some of his extraordinary colleagues, Alan Perlis, Alan Newell, really founded the School of Computer Science and the tradition at a very early stage, and developed a group of people who developed some of the first ideas about artificial intelligence. A lot of early work on programming languages and software engineering happened here. So it's been a fabulous experience being here at Carnegie Mellon around all this history, and of course, so many exciting things going on today. The Institute for Software Research is one of, I believe, 7 departments within the School of Computer Science. We teach undergraduates, we do research with Ph.D. students, We do various kinds of outreach to the community. The Institute for Software Research is really about, in my view, where people meet software. So there's software engineering side, which is mostly where I sit. It's about making people more effective at building software. And my colleagues do everything from, studying the process of developing open source software and, why that works as well as it does. Also tearing down some misconceptions about open source software. Many guys do not always find more bugs because we all sort of miss the same ones. But nevertheless, these systems work in a very interesting distributed way that now companies are learning from. Carnegie Mellon's been at the forefront of that. Of course, building better languages, that's something I'm tremendously excited about. We have people like Claire Legues building tools that automatically repair code. So it's an exciting group to be in. The other side of kind of where people meet software is what we call societal computing. We have a Ph.D. program in societal computing, actually, as well as software engineering. And societal computing is really about making software that solves societal challenges, right? How do we understand social networks, both kind of literally social networks like Facebook, but also networks of communication among people electronically, phones, by email? How do we analyze those and see how people are working together in an electronically enabled world? The whole School of Computer Science has people working on security, but in the Institute for Software Research, we work on usable security. How should you choose a password so that it's easy to remember and it has the right security problems? It's hard to guess. So we've done some of the basic work in figuring out the guidelines that you should replace your password every few months is actually a bad idea, right? Because that leads you to have to write down a password or choose one that's easier to guess. And so, maybe better than changing it all the time and having weird symbols in it is just having a longer password, right? Because then you can come up with something that's a phrase that's easy for you to remember, but because of its length is hard for other people to guess. Also, issues like privacy. How do we deal with privacy in the world of the Internet of Things, devices all over the place that have our data and need to share the data to analyze it, but yet we would like to not have the world be intrude on our privacy in kind of surprising or harmful ways. So I think it's a really fun department to be in because there's this combination of kind of understanding software at a very deep level, but also understanding interactions with people and how we build software to really enable people to be everything that they can be.
Taking a step back and going to the basics, how do you define a programming language? What are its core elements?
So I think there are a number of views on programming languages. From a technical viewpoint, programming languages can be viewed as, and historically have been viewed as, syntax and semantics. What are the things you can say? How are those structured up, in a grammar? And then what do they mean, right? And meaning has the aspect of what does it do when it runs, but it also has to do with, what makes up sensible programs. And so for statically typed languages, we have type systems that define what programs make sense. This is, I think, traditionally what the academic world has focused on. How do we carefully define these things? The industry world has been more pragmatic. I mean, we have some languages out there that are kind of defined by their compiler, which kind of works, but can cause problems later when you find out that, well, the particular choices in this implementation weren't very well thought through, and we have all these security problems, right? Eval and JavaScript and all that. So I think, thinking about those core elements carefully really makes a lot of sense, and it's exciting to see some of those elements of careful thinking about the syntax and the semantics moving their way into industry. We have the next, I think, exciting standard in the world of programming the web is WebAssembly. So all the browsers are building this in, and it's I think going to enable more powerful and high-performance programs to run in your browser. But it's all specified using programming language theory. It's very exciting because we really need something that's high-performance but also highly secure. And these careful definitions, I think, really enable us to get there. There's another side of programming languages that I think has maybe been understudied, especially on the academic side. That really connects to the people side of software engineering. Language is a tool, but it's a tool used by humans. It's a tool used to communicate between the engineer and computer. To carry programming languages forward, we really need to look at the way people think, the way that they engineer software, to actually incorporate some studies of people into the way that we do programming language design. Actually, some of the work that, one of the big themes of my research and some of the people I work with is finding out new ways of studying people interacting with languages and then making the languages better so that people can understand them and use them and make fewer errors and be more productive.
In this regards, combining the elements of being maybe the theoretical side and the people side, is there an ideal programming language you think about?
Well, we're working on one. I think it's a challenge to say ideal because there are so many settings in programming. So I don't know that one language will be good for or ideal for every setting out there. There are different pressures in kind of a systems context where you care enormously about control and performance and sometimes, the ability to do low-level things because you're interacting with hardware versus applications programming where often developer productivity is paramount along with kind of the user experience. You really want the ability to iterate quickly, to change code more rapidly. And that conflicts to some extent with the high degree of control that you might need in the system on the system side. I think we're developing a better language. I work mostly in the application side of that divide. I do a little bit of work in domain-specific language design where you might be designing a language for a particular task that is not general-purpose programming. For example, we have one for diagramming that I can tell you about a little later on in the conversation. There are principles that we can use across these languages. So we've really been trying to discover what some of those principles are, and hopefully they can be incorporated into the next generation of industrial languages.
If you decompose a programming language, what are inputs that are required to actually create one in simple terms?
So a language, first of all, it's a grammar. It's the symbols that you use to express your ideas, symbols for math, symbols that talk about the abstractions, building objects, building functions, and then the syntax that you put those together. How do you talk about the definition of a function, the definition of an object? How do you talk about the definition of a module or a component? How do you talk about, types? What are the kinds of things, kinds of objects in your language? You need to think about that and have a way for programmers to express those things. You need to think about how does the program run? What's the mode of operation? I think traditionally we think of programs as kind of step-by-step instructions and execution, and so you talk about what comes after what. But there's also concurrency models where you might be doing two things at the same time. And you have to think about what are the mechanisms for combining those concurrent mechanisms, those concurrent operations. You might have a completely different paradigm that's based around search, right? So logic programming. In logic programming, you're really, searching for the answer to a query. And logic programming is, I think it was kind of a niche for a long time, but it's becoming very important in databases and, big data applications now, as well as even applications like program analysis, which is close to my field. So you have to think about the way the program executes as well, whether it's in a step-by-step way or in a kind of a search mechanism, and how do you coordinate that? Out of these elements, then you think of how do you build larger structures out of those modules, how the modules connect, processes or threads, and how you coordinate them. That's where you get into the higher level ideas of software architecture, which is definitely an area that's exciting to me and one place where I've done some of my research.
We're curious about programming languages through a historical lens. So today it's 2019. There are a flurry of programming languages. Why do you think the evolution of programming languages took, the path it took, and why is there not one to rule them all?
That's a great question. One of the reasons programming languages are compelling to me is that they're the programmer's most basic tool. the first thing you have to do is find a way to talk about your program and to express your program to the computer. And the language helps you do that. So it's so incredibly fundamental. A result of this is that it's hard to change. If I learn programming languages and I write software in it, and then maybe there's a different language that comes around, it's hard for me to switch to that because I've spent a lot of time learning the old one, I've written code in it, and it might be hard to reuse that code with the next language. There's a big network effect with languages. You want to have everyone in the project using the same language. So languages are sticky. They tend to change slowly and hang around for a long time. Organizations spend quite a bit of time kind of moving from one language to another. But yet you see generations of changes in languages, from the first assembly languages that kind of freed us from programming in binary to Fortran and COBOL that gave us the ability to program in high-level languages for the first time. Fortran is formula translation. Wouldn't it be amazing to program in terms of math instead of instructions? But then, of course, you get object-oriented programming and functional programming coming out. I think you see transformative effects in industry from technologies like garbage collection. But garbage collection took 30 years to go from the initial developments in Lisp in, I believe, even the 1960s until the 1990s when Java came out and garbage collection technology was finally good enough to be used in a widespread way in applications languages. So it's a long path, and partly it's because the problems are hard, right? Lots of problems had to be solved with garbage collection to get it to work well enough. We had generational and incremental collection and so on. But there's also this kind of latency built in because programming languages are such a basic tool, and it's hard to switch. Even though, as a researcher, maybe my ideas might take longer to get into practice from in the field of programming languages, I think it's exciting because you see the transformative effect that languages can have. The ability to program seamlessly on the web in JavaScript, the ability to program in a garbage-collected language, as I mentioned. And I think we're seeing similar things coming out in the languages today. Safe systems programming in Rust in a kind of a high-performance setting. The ability to build languages that incorporate code generation in flexible ways through Scala, for example. Metaprogramming that you see in powerful facilities in Ruby that make Ruby on Rails a compelling framework for a lot of people to use. So these are all technologies that often come to industry in imperfect packages.
Yes.
So, some aspects of Java were obsolete when it came, let alone now. But nevertheless, they have this big impact. And I think there are future technologies that can do the same.
From an adoption standpoint, you did mention that the change is hard for industries, even for programmers. What do you think are the elements of a programming language or people's behavior so that they adopt one language and it becomes very popular versus other language which may have more capabilities that doesn't get adopted as much?
Programming language adoption is a social phenomenon, partly. It's social and technical. Partly what attracts people to a community is the other people in it. Obviously, the technical aspects of the language make a difference, but different people are attracted to different things. There's a lot of people who love functional programming because it's so mathematical. Other people love object-oriented programming because it models the world so well. They find the abstractions very intuitive. Some people like systems programming because of the degree of control they get. I've heard of companies hiring people from one community because they feel that community is strong. Some companies have become functional programming shops because people who have good mathematical skills like functional programming languages get a lot of those programmers will program in maybe an obscure functional language like OCaml or something. OCaml is not nearly as obscure as it used to be. I think that's one of the exciting things in that area. But you can kind of get ahead through this niche. I think our industry is actually full of these niches, which are partly social entities and partly technical entities. Often how change happens is actually from people getting excited about a new language and finding a niche where that language is really good, they can be productive and build interesting things with it. And then other people see what they've done and get excited about it, and you have something that expands the reach of the language. I think the open source communities and excellent libraries make a big difference. I think a lot of people program in Ruby because of Rails. A lot of people are interested in Scala because of the great higher level language, the higher level libraries that are provided and that are enabled by the language features in it. The libraries and people's enthusiasm, willingness to kind of pitch in and make the libraries better is also a key part of programming language adoption.
You've also done some work on using an interdisciplinary approach to programming language design and how important it can be. Could you talk to that element and how you've used it in your research?
Absolutely. So I think an interdisciplinary approach to programming language design is really key, I think, to building the next generation of more effective programming languages. We've known for a long time, especially in the academic world, that some key ideas in type systems, in language design, could have transformative effects. If we can say more about the properties we want our programs to have, for example, with a type system, or maybe in a logic, if we can structure our programs in more effective ways, then we could build better software that will make the world a better place. But so often, these technologies get stuck in the lab. How do we make that transition to practice? A lot of it is because we understand the technical side, we understand the math, but we don't always understand the people. And so I've been working with Brad Myers in human-computer interaction here at Carnegie Mellon. My colleague Joshua Sunshine, the goal of his overall research to integrate the study of people and the study of programming languages. And we have a wonderful student, Michael Koblenz, who's working on the Obsidian language for smart contract blockchain programming. We're trying to forge a new way of designing languages. We don't want to get rid of the math, because the math is what enables us to get guarantees that the language is well designed, that the programs don't have certain errors. But we want to find ways of making that those mathematically based constructs accessible to humans. And so we're doing iterative studies as we design this blockchain smart contract programming language to see if programmers, even programmers without a lot of experience, because maybe business people want to write smart contracts, we bring them into the lab and we show them prototypes of our language. And we ask them, what do you think this construct means? What do you expect it to do? Or we give them a problem and we say, what do you imagine code that solves this problem should look like? So we get an idea of what is natural for them to express. And then we try to merge this natural expression of programs with the mathematics and say, okay, how can we make these two compatible? How can we make a language that expresses things the way programmers expect them to be expressed, that isn't confusing to programmers, but also is sound mathematically and gives us a language with the properties that we want. And we believe that with this new design approach that iterates between the user studies, trying to make sure programmers can understand these things, they don't make mistakes with them, and the mathematics that studies the foundation of the language itself and the properties, we can get a language that is easy for people to use, avoids people making kind of unintentional mistakes, and really allows us to write programs that don't have this kind of bugs that are ubiquitous in today's software systems.
So on that topic, to what extent do you believe this framework of having a more human-oriented and user-centered approach is used or adopted in the world today?
So I think it's something that people are just exploring. We're exploring it. There's a few other research groups that are looking at it. There are a few groups in industry that do some of this too. So user interface testing is now quite common in industry. A lot of that hasn't been applied to programming languages yet, but there are some pioneers who are starting to do it. I think it's really something that is emerging, just kind of in the corners of industry and of academia and of industrial language design. And I think it's going to become more common because we've seen it used successfully in other fields. I think we have to, the techniques are there, but we have to figure out how to adapt them to this area of language design. Language design is a little different than testing out a user interface. When you test a user interface, you're often trying to make it accessible to novices. Whereas a programming language, there are programming languages for novices, and maybe the techniques carry over more directly there. But for many programming languages, we're looking at expert programmers may have years of experience, and we want to make them more productive. But the language is a very complex thing. The programmer has a lot of experience in other languages. Maybe they've been traumatized by the problems with previous languages. And so we have to kind of work through all that complexity, suss out, what are the elements of this very complicated language design that make it more effective for these expert programmers to use or not. So I think that's really what the challenge is in trying to come up with these new methods of designing languages. How do we isolate the pieces that really help make people more productive? How do we show that actually works? And how do we synthesize a language design that makes sense in the big picture of things, where all the math works out, where kind of the edges work with the way humans work, and really is effective for the task at hand.
It seems like design of programming languages learned from how startups are being built, building an MVP first based on user research and melding it with the mathematics and sciences behind the scenes.
Absolutely. Yeah, I think the minimal viable product is absolutely applicable to language design. And iteration, right? Rapid iteration. We've known this for years, that field of software, that an iterative process, an agile process, helps us understand what we need better. And I think for a while, there was a perception that the need to get all the math right, or maybe the need to build a big compiler, kind of got in the way of that. We can actually prototype compilers and interpreters quickly. We can do prototypes with users even on paper before we build a compiler at all. If we understand the landscape of the math, we can generally get things right while we're prototyping. We don't have a guarantee of it. Maybe we need to come back and do a proof that everything works at the end. But one of the great things about having a whole field of programming language research is we have a ton of information to draw on about what makes a sound type system sound. So we can use the principles and apply them in kind of this rapid iterative fashion with a fairly high degree of confidence that when we come up with a design, it will be sound when we check it for that, or it will be something we can make a few tweaks to get all the math just right in place at the end.
When it comes to software development, there is an element of software process, there is developer productivity, there is software quality, which is an outcome of software development process. How do you define software process, developer productivity, and software quality?
Yeah, that's a great question. These things are hard to measure because they're multifaceted. You have to keep the many facets of that in mind when you develop programming languages. From a point of view of research, we try to find ways of quantifying that. And of course, they're imperfect ways, but we bring programmers into the lab and we have them do some task, right? A programming task. And so we measure productivity in terms of, how long it takes them to do the task. We can measure quality in terms of, the bugs that might be present when they finish. And, hopefully we can show an effect of some new technology, some new language on making people faster or reducing the bugs that they produce. So I think that's as part of it. But of course, that's still programming in the small. The best we can do in a lab is probably bringing one programmer in for, an hour or two, or maybe a day at most, and giving them a task and watching them perform on that task, measuring their productivity and so on. But we also have to keep in mind the bigger picture. The fact that programmers are communicating with other programmers, that they're iterating on designs, And that a lot of the challenges we see in software development actually come from that. Delays happen because, we don't communicate well enough with our customers, or bugs happen because programmers get protocols wrong at boundary components. And so they kind of work well in isolation, but we put them into a system and there's these kind of surprising effects that come out of it. And so I think there's a role for programming language and software engineering theory. Going back to David Parnas's classic work on how do you decompose a system into modules, Parnas's answer was that each module should have a secret, and that secret has to do with something you might want to change about the software. Data representation, the algorithm that you use, the choice of a user interface. And so that module encapsulates that secret and hides it from the rest of the world. And then the interface to the module serves as kind of the stable point. So this is classic software engineering theory, but I think we can use it to drive programming languages. We already have types and module systems which have built on those ideas for a long time. But if we want to think about how do we make programmers more effective in a process, in the large, when they're building complex software systems, I think we need to think about that software engineering theory and say, how can we do better at documenting those interfaces between modules? How can we help programmers better hide those secrets so that we don't get unexpected dependencies from other components on those? How can we help programmers, reason locally based on their module and the interface of other modules? How can we help programmers communicate the design of their systems more effectively? So I think if you look at those ideas, many of which came from software engineering, and you look at how can we actually express those design ideas inside a programming language, you can make progress not just at the small level, the level of small programming tasks, but at the level of larger system building tasks that whole teams of programmers might work on together.
Honing in on this notion of measurement, in a bit more granularity, what type of metrics would you use to measure developer productivity and software quality?
There's an enormous variety of metrics that have been used. At the level of software teams, you can use lines of code per hour. You can also try to talk about features rather than lines of code, because what the user wants in the end is features. I think those things they're all imperfect. If you just measure productivity by lines of code, then I can write really long programs that don't do very much.
Yes.
So it's all a matter of perspective. When we study programming language designs and productivity, that's one reason why we focus on tasks. We say, implement this function to do this specification, implement this data structure. For example, we did a study with immutability, type system for immutability a few years ago. This was part of this project of interdisciplinary language design. So we had programmers implement some function. One of those functions was returning a list of data from a data structure. Another one was making a data structure that was mutable, making it immutable so it couldn't be changed. This is a task that should be within the range of any programmer, but there are some things that make it tricky. So if you have an array in your data structure and your constructor for the data structure takes in that array, you might be tempted just to take the array and assign it into the data structure. The client who passed through that array, they might still have a copy to it. And then if they can change the data in that array, then your data structure is not immutable. It can be changed from the outside in a surprising way. And so in a language like Java or C#, the handling of arrays has to be done very carefully when you want to create an immutable abstraction. And so we looked at how often do people make these errors. It turns out they make them fairly often because it's kind of an easy thing to overlook that you need to actually copy the data when you bring it into the data structure rather than just using the same array. And we also found that then, the tools we were developing, the type system we were developing, could help programmers avoid making that mistake. Programmers are really good at solving problems and coming up with creative designs, but they're really bad at following rules consistently throughout a large programming task or a large code base. And that's exactly what computers are good at. Computers are good at enforcing rules and consistently doing the correct thing, but usually on very simple tasks. Part of what we were doing in this project was coming up with a set of rules that help programmers get things right and kind of remind them when they don't have something quite right. And so we measured productivity. We measured, how long does it take to do these tasks? Then whether they do it with many lines of code or few lines of code, that doesn't make any difference. It's just, did they do the job or not? And then whether they made errors, whether they actually produced a data structure that was immutable and had the right properties, or whether there was some mistake where they had left out something, check or a copy that they needed to do.
Became more the outcome one was looking for, and if that outcome was achieved in a way which it was expected to be.
That's right. Did they solve the problem? Did they complete the task? And was their completion correct? Obviously, this is kind of a micro-level view, but it's one that we can have pretty high confidence corresponds to not a big task in programming, but a real task that people do, right? People need to develop data structures. People write algorithms. And I think measuring, do they actually do that correctly, and how long does it take them to do a task of fixed length, that's a good starting point. And then now you can do comparisons. You can look at how does technology affect that? Potentially, how does process affect that? It's not something we study so much, but you could look at that as well.
Do you think there's a bias or irrational, even bias towards elegance in this community?
Well, I definitely think there's a bias towards it. I think that's across all of computer science. The idea of keeping code small and simple and beautiful, that's something that's, I think, just attractive to programmers and maybe to engineers in general. And it's true in programming language specifically. What are the languages that people really love? Well, they're often languages that are simple and powerful and have this elegance. The storied languages of computer history, right? There's Lisp, and maybe particularly Scheme, which is the kernel of Lisp. There's Smalltalk, which is kind of an ideal object-oriented language, also very simple. Everything is an object, everything is a message. There's no primitive built-in data types. There's, the essence of functional programming, or typed functional programming, maybe in the language ML, or Haskell. It's the essence of lazy programming. So these ideas of elegance are definitely popular. I think it can be taken to extremes. You can say, well, I'll take elegance at the expense of everything, and then you sometimes get a language or a system that's elegant, but it's just missing things you really need to do. I think some of the more pure functional languages sometimes fall into that trap a little bit, and probably Smalltalk did too on the object-oriented side. But it's also true that this quest for elegance, it drives us towards better designs. The problem in the pure functional language isn't necessarily the purity or the focus on elegance, but in my view, realizing that functional programming is great, but for many applications, it's not all about functional programming. We need abstractions that combine multiple functions. I've always been a little bit countercultural in the academic community because I work on object-oriented languages. But I think if you take the great divide between object-oriented languages and functional languages, we're really arguing about something we shouldn't be arguing about, because the essence of objects is actually a collection of functions. It's the methods that you use to access the object. Mark Miller, whose work I admire in the area of object-oriented programming, views an object as a multi-entry function. It's a function that you can call several different entry points to get different behavior of. And I think that connects with the history of object-oriented programming as well. Alan Kay didn't really talk about inheritance or state as being characteristic of objects. He talked about messages. What are the messages you can send to an object? And I think that's actually very close to functional programming. So what we need is maybe not focus on one paradigm or the other exclusively, but we need to find abstractions that make both paradigms work together. And that's one of the things that I really love about the design of Scala, which is one of the languages that's influenced me in many of the languages I'm designing now, is how well it combines these two paradigms in a way that I think preserves the elegance of both of them.
Is there a checklist as to how one can apply developer productivity and software quality when it comes to software development process in the industry?
So I think there are checklists to think about. I don't think a checklist alone is sufficient because so much depends on context. And the way you solve a productivity problem the way you enhance productivity depends on the property you're looking at. So one example from language design is lower level versus higher level tasks and errors. Mm-hmm. So you can have different kinds of problems that might come from your language or might be solved by your language, right? And some of them are low-level barriers. The question of, how do I get the object that I need? There was a study by my colleague Brad Myers that shows that new statements and constructors are easier to use than factories, because with a factory you kind of have to search. You have to search for the method that creates the thing you want. And that could be hard, right? That factory could be somewhere that's difficult to find in your source code. But if you use a constructor, then the way to create the object is always packaged right there with the class that you want to use. And so it's there with the functionality. There's kind of low-level problems with how does the developer do the next task? And how do we make that easy in a language? Of course, there are software engineering benefits of building things based on factories. Maybe you still need to allow people to use the factory design pattern sometimes, where you have a function that creates an object and you call that function rather than calling the constructor directly. But now maybe you have a tool in your IDE that allows you to search for methods that return a particular kind of object. And so maybe then you can get the best of both worlds. You can have your factories for software flexibility, but you can also have kind of usability. There's many ways of solving the problem, but in that context, you bring developers into the lab and you look at them performing a very small task, and you see, what are their barriers? Where are they spending their time? What are they thinking about? You ask people to talk out loud in the lab about what thoughts are going through their head, and you start to see what are these problems, and then maybe you can change the language in certain ways or add tools in certain ways that fix those problems. That's kind of a low level of abstraction. There's a higher level of abstraction as well that impacts productivity. Again, I'll use the language context because that's where I've really studied productivity more. But this has to do with mistakes that people make as they're building a large system. And it's not that they're trying to do something and they get stymied because they can't find which object to create. It's more that they're building their code and they're oblivious about some property that they need their system to have. So I'll give an example from the world of smart contracts, which is where we're building the Obsidian language. A number of prominent smart contract errors have come about because of reentrancy or unexpectedly calling into a contract, maybe when the contract is doing something else. So this was the origin of the DAO hack. You're performing one operation on a contract, and kind of in the middle of that operation, you call into it again in an unexpected place, and you can steal money from the contract by doing this. We're developing this language, Obsidian, that captures the intended form of interactions between the contract and the outside world. It says, what are all the operations on the contract, and when can you call them? When you first create the contract, maybe only a few of your operations are available. If your contract is buying insurance, then the first thing you have to do is say what you want insurance for, and then the insurance company has to put in a bid for how much insuring that thing will cost, and then you have to accept the bid and pay money for the contract. And then later, if the thing you got insurance against actually happens, then you can call in and say, hey, this bad thing happened to me, I need my insurance coverage for it. And so there's this sequence of things that happens in a smart contract. And so in previous languages, if there were any of those restrictions, you had to code them up yourself. And, guess what? Programmers are humans, and humans are not good at consistently checking everywhere that things are right. And so someone screwed up and people stole tens of millions of dollars from this DAO contract. What we're doing is we're saying, hey, when you design this smart contract, think about what are those operations. Think about the order in which they can be applied, and then our language will enforce it for you. You don't have to worry about making that mistake. And so there's this other side of productivity, which is studying humans in context and looking at the errors that they make, and then designing tools that kind of assist them at avoiding those errors.
And this bleeds nicely into our next segment, which is your work, your current projects, which we find incredibly fascinating. And we also find it fascinating how you find time to work on all these projects. You mentioned Obsidian, which is really interesting. It's a safer blockchain programming language, smart contract language. There's also this project called Wyvern. Talk about that. What was the genesis of it, motivations?
Absolutely. So Wyvern is motivated by all the problems we have in both productivity. How do we manage building large systems? But then also, how do we do that correctly, particularly in a world that's full of attackers? So security is an ever-increasing problem, and we just find it so hard to avoid making these mistakes. I mentioned the DAO hack in the smart contract area, but in more general purpose application code, we have continual problems with buffer overruns and cross-site scripting and command injection and various problems of this sort. And a lot of these problems, they come down to the same issue that to avoid these problems, programmers have to follow these rules as they develop consistently, and we're just not good at doing that. I believe this is an area where language can help, and particularly an understanding of software design and process that we were talking about earlier can make a big difference. Talking specifically about the languages, let's take command injection, which is something like buffer overruns. Okay, if you switch to a high-level language, you can get rid of buffer overruns, or at least, turn them into errors that are kind of safely caught and dealt with. But command injection is still a problem even in very high-level languages. It's really a problem of abstraction, I believe, in the same way that buffer overruns are a problem of using the stack as your array or smart contract. We have a contract that you can call any operation on, but you don't actually write down the order that you expect them in, the calls to come in. I think in the same way, something like command injection is a failure of abstraction. With command injection, there is some kind of little language in your program. That little language might be the language of the shell script for doing operations on your server. Could be the language of SQL for doing operations on a database. Could be a regular expression language. But whatever it is, there's a language internally that you're using. You're getting input from the user, and you're using it to construct something in this language. The problem of command injection comes when that end user, they inject a command into the data that they're giving you, and you don't realize that there's a command in it, and they own you. But the problem is that inside, when you're engineering this code that uses this little language, you're not really using a language. You're like pasting together strings to form a SQL query or a regular expression or a command for the command prompt. We can do better. Language technology, we know how to build languages that are not just strings. They have parsers and type checkers and all sorts of things like that. But we can't use this technology because our languages are fixed. In Java, I just have Java code, and if I want to write a database query, the only way to represent it is with a string or maybe with a data structure. It tends to be a bit cumbersome. So what we'd like to do in Wyvern, and what we've been exploring, is a way of putting other little languages into the host language of Wyvern. Say you can switch to SQL mode or to regular expression mode or to command prompt mode, and then in a block within your programming language, you're just writing SQL. So now the host compiler can jump to a plugin for SQL, and it can have the SQL plugin parse that SQL code and do it in a safe way so that when, if an attacker were to try to put in a command, we don't parse that command. It's treated as data. We only parse the code that's actually embedded in the host language, in Wyvern in our case. So we can just avoid this problem of command injection. And the wonderful thing about it is that you're actually using the SQL programming language inside Wyvern, and so you can get checking for parsing errors, you can get ID autocomplete. So we haven't built all that for SQL in Wyvern yet, but we've prototyped it in some other settings. So you can actually get a better user development experience from having this ability to deeply build in languages, little languages, into the host language. And so with this better abstraction, you can get both higher productivity for programmers and also safety. You can get complete immunity from command injection attacks, as long as every time you use a little command language, it's actually a real embedded language and not just hacking some strings together.
What is your research methodology, are there any frameworks you apply to your research?
Based on this idea of interdisciplinary research design, we actually use a number of different kinds of methods. For the mathematics of language design, we use conventional tools of type theory and proof. We write down the formal definition of the language, or maybe a core subset of the language, and then we use the tools of type theory to prove that nothing will go wrong when the language executes. And so that's how we get a safety guarantee for the part of Wyvern that integrate sub-languages, domain-specific languages like SQL with the host language, and also higher level properties. So another thing Wyvern is doing is reasoning about program structure. And so we have theorems about program structure that we can prove using, again, type theory. But then we have tools from other disciplines as well. We use, when we want to find out whether a language works at scale with larger programs, then we use a case study methodology, which comes from social science, trying to take a realistic setting, a realistic program, write it in the language that we're developing, compare it to a version of the same program in some other language, and look at the differences. So they can be quantified in various ways through maybe counts of lines, how many lines are in the program in the new language versus the old language. You could look at structural things, how well are different concepts encapsulated in this language versus the other language. That gives you a notion of modularity. And then, of course, we have human-focused techniques, like I mentioned earlier, bringing programmers into the lab, showing them alternative language designs, and trying to understand which one helps make those programmers the most effective. These are also kind of social science-based qualitative research techniques.
So I guess there is a 360-degree view of application of the research you do.
That's right. Basically we try to look at what are the properties we want in our language. Well, we want it to be mathematically sound, so we apply mathematical techniques. We want it to be usable by programmers, so we apply kind of social science techniques looking at humans. We want it to apply in the real world, so we use these case study techniques that are study application of technology in a real setting. So it's really a view of matching the research methodology to the property that we're trying to get in the language that we develop.
How has technology impacted development of programming languages, software productivity, and software security?
I guess there's multiple ways of looking at this. There's the impact on language design itself, which, of course, in developing a language, we use all the techniques of standard software development, as well as the research techniques I mentioned. We have open source development and agile approaches, but then there's a broad variety of language tools we use as well. Parsor generators, there's proof assistance now that you can use on the theory. There's technology that we use for the user studies. We're doing a study on Mechanical Turk right now, or let's see, I guess it's not Mechanical Turk. We're using online surveys. We apply technology there. I think there's also the other side, which is the impact of programming languages on industry and also of research on industrial programming languages. This is a long time horizon, but we're starting to see some of the ideas we've explored in our research make it into industry. One example is Rust. Actually, an early version of Rust had type state, which is the idea of encapsulating the protocol of interaction between components, which we're exploring in Obsidian. So Rust, actually type state wasn't quite ready to go into Rust, but Rust has ideas of ownership. And those same ideas of ownership are ones that we kind of initially explored for type state. We weren't the only ones exploring ownership. We didn't invent the idea, but we moved it forward and other researchers moved it forward. And now Rust is taking ownership and making it mainstream for managing memory in the context of systems level programming. So I think it's really cool to see, some of these ideas we've been working on start to have an impact. One of the reasons I'm excited about Obsidian is that it's such a new area. There's new blockchain and smart contract platforms coming up all the time. And so people are still figuring out what technologies to use. And so I think there's room for a new language like Obsidian. Whether or not Obsidian takes over the smart contract world, the world there is changing so fast, new languages are being proposed. I think the ideas we're proposing with state-oriented programming are ones that could get a foothold and kind of transition into industry and make an impact relatively quickly from research to practice there.
Today, there's a lot of value that flows to code generation. So programmers today who generate code based on some architectural design capture a lot of the value. You can look at salaries at Google and Facebook for even junior developers. At what point might developers who generate code become obsolete, or where most of the value flows to architectural design?
That's a great question. I think one of the beauties of software development is that the power we can get from abstraction is essentially unlimited. If you look at the history of programming, you'll see technology after technology has been used to generate code. You can see this. There was a belief that we could make software factories and generate code based on ideas of factories. People fear that code generation leads to programmer obsolescence. But what actually happens is that what we're then doing is we're designing the generators. When we figure out how to do that in a principled enough way, we've developed a language, and the generator is just a compiler for that higher level language. And then eventually we'll start to generate code in this higher level language, and we'll make this generator more flexible and adaptable, and we'll start programming the generator, and then that generator will turn into a compiler for a yet higher level language. And I don't have any reason to believe this is going to stop. I think the story of computer science has been developing one abstraction on top of another, each of which makes us more powerful and empowers us to build better and better applications that extend the reach of computer science and extend the reach of humanity. And so I think really this is a story of success that's going to continue. And the way that we manage it is we climb this rising level of abstraction. I don't think it's going to take away our jobs. I think it's going to enable us to do new things that we couldn't imagine before, that's going to create more and more value.
Moving on to the last section, our outro section. What motivates you?
So like many engineers, I love to build things. But I think what really excites me is finding new and better ways to build. And that's why I like building tools. I like building languages. I'm in the university. I also love working with students, full of energy. They're full of new ideas. That really keeps me inspired. And it keeps me on my toes too. So it's super fun.
How do you allocate your time?
That's super challenging. It's something I struggle with because as a professor, you're teaching classes, you're working with students, you're volunteering to read papers and organize conferences for the community. Really, it's a matter of prioritizing and kind of dividing up your life. How can I make sure that I kind of make progress in all the domains of service and teaching and research? And then within each domain, then I look at the priorities. What is the most important thing for me to be doing, to support my students, to help them reach their full potential, to push this technology out into research, to revise this set of lectures so that I can communicate these ideas to our students more effectively. It's a continual challenge. One of the things I've learned, I think I learned relatively late, is that despite kind of this infinite sense of possibility that we get from research and from computing and from abstraction, my own time is limited. So I have to pick and choose what to focus on and, what's going to make the most difference in the world.
Which non-consensus views do you hold near and dear?
I already mentioned one. I think versus maybe the academic consensus, which really centers around, the beauty of functional programming languages. I can appreciate that, but I believe that objects are incredibly important in addition to functions. I wrote this controversial paper a few years ago that says why objects are inevitable. The theme of the paper is interoperability and extensibility, and it basically says ideas are behind extensible systems. Everything from Linux kernel drivers, which are written in C, which you can plug in to your operating system in new ways, to iOS and Android applications. They're just big objects. If we didn't have objects, we'd have to invent them. I think that's incredibly important, and we need to figure out how do we merge ideas from OOP with powerful ideas of functional programming to make something with the power of both.
What's the biggest trade-off in your professional existence?
It's challenging balancing all these elements. I love to build systems. I love to work with students. I love to teach. I love to develop new ideas and prove that they're worthy even beyond the system that I'm building today. I'm lucky I get to do a bit of all of those things. Figuring out, which one to focus on is hard. There's the opportunity there.
What are you currently reading?
So I'm currently reading the book Why We Make Mistakes by Joseph Hallinan. That's a lot of fun, and it actually ties in pretty well with my research because a lot of what I do is develop languages and type systems and tools that help head off some of the mistakes that we make. And so really understanding what is it about our humanity that causes us to miss things. That's one of the themes of Hallinan's book, and really one of the things that I'm trying to help avoid in the context of computer science and programming.
Are there any other projects you're currently working on beyond Obsidian and Wyvern that you'd like to highlight?
One of the latest things we've been doing, which has been super fun, is a project called Penrose. This is a collaboration with graphics professor Keenan Crane. And what we're trying to do is develop a new programming language for mathematical diagramming, or really any kind of technical diagramming. You might have an expression that is sets and you want a Venn diagram, or you have some kind of manifold that you want to visualize, or you want to look at how rays trace through an environment. We want you to be able to write an expression, a mathematical or technical expression, just the way you'd write it in math, and then have a way of styling that into a diagram so that you can take the same mathematical expression and view it multiple ways. And we want to use all the ideas of graphics and optimization to make that diagram beautiful right out of the box. So you don't have to spend hours and hours tweaking it to get exactly right in Illustrator or something. So this is a super fun project. Gets me a little out of my space of programming and towards being people learn or appreciate mathematics through better diagrams and illustration.
How can listeners find out more about your work?
Probably mostly from my website. If you search for my name, Jonathan Aldrich, you'll get to me pretty quickly. As an academic, I produce papers, but we also have links to our open source projects, Wyvern and Obsidian and Penrose. That's probably the place to look. I keep hoping to start a blog, so stay tuned.
We hope you enjoyed the conversation. For more information and latest updates, visit us at luminary.fm or follow us on Twitter at luminaryfm. Please subscribe to the podcast, pop us an iTunes review, and share with friends. Don't forget to check out the show notes. And a quick disclaimer, the views and opinions expressed in this episode by the hosts and the participants are solely those in independent capacity and do not in any way represent the views from any organization, company, or management they may be associated with. And thank you for listening.